At the end of this video, you should be able to discuss Louis de Broglie's role in the development of the quantum model of the atom, compare and contrast the Bohr model and the quantum model of the atom, and explain how the Heisenberg uncertainty principle and the Schrödinger Wave Equation led to the idea of atomic orbitals. Chapter 4, Section 2, the quantum model of the atom. To the scientists of the early 20th century, Bohr's model of the hydrogen atom contradicted common sense. Why did hydrogen's electron exist around the nucleus only in certain allowed orbits with definite energies? Why couldn't the electron exist in a limitless number of orbits with slightly different energies? To explain why atomic energy states are quantized, scientists had to change the way they viewed the nature of the electron. Electrons as waves. The investigations into the photoelectric effect and the hydrogen atomic emission revealed that light could behave as both a wave and a particle. Could electrons have a dual wave particle nature as well? In 1924, the French scientist Louis de Broglie asked himself this very question, and the answer that he proposed led to a revolution in our basic understanding of matter. De Broglie pointed out that in many ways the behavior of Bohr's quantized electron orbits was similar to the known behavior of waves. For example, scientists at the time knew that any wave confined to a space can only have certain frequencies. De Broglie suggested that electrons be considered waves confined to a space around the atomic nucleus. It followed that the electron waves could exist only at specific frequencies, and according to the relationship E is equal to h nu, these frequencies corresponded to the specific energies, the quantized energies of Bohr's orbits. Other aspects of de Broglie's hypothesis that electrons have wave-like properties were soon confirmed by experiments. Investigators demonstrated that electrons, like light waves, can be bent or diffracted. Diffraction refers to the bending of a wave as it passes the edge of an object, such as the edge of an atom in a crystal. Diffraction experiments and other investigations also showed that electron beams, like waves, can interfere with each other. Interference occurs when waves overlap. This overlapping results in a reduction of energy in some areas and an increase in energy in others. The effects of diffraction and interference can be seen in Figure 4-10 on page 99 of your text or on the screen now.
In 1924, Louis de Broglie proposed that electrons, like light, had properties of both particles and waves. De Broglie suggested that electrons be considered waves confined to the space around an atomic nucleus. De Broglie suggested that an electron would have a characteristic wavelength equal to Planck's constant divided by the momentum of the particle. It followed that the electron waves could exist only at specific frequencies equal to energy divided by Planck's constant. These frequencies corresponded to specific energies, the quantized energies of Bohr's orbits. 3 years after de Broglie's proposal, C.J. Davison and L. Germer discovered that electrons can be diffracted by a single crystal of nickel. This important discovery provided the first experimental confirmation of de Broglie's theory.
The Heisenberg uncertainty principle. The idea of electrons having a dual wave particle nature troubled scientists. If electrons are both particles and waves, then where are they in the atom? To answer this question, it is important to consider a proposal first made in 1927 by the German theoretical physicist Werner Heisenberg. Heisenberg's idea involved the detection of electrons. Electrons are detected by their interaction with photons. Because photons have about the same energy as electrons, any attempt to locate a specific electron with a photon knocks the electron off its course. As a result, there is always a basic uncertainty in trying to locate an electron, or any other particle, The Heisenberg uncertainty principle therefore states that it is impossible to determine simultaneously both the position and velocity of an electron or any other particle. Although it is difficult for scientists to accept this fact at the time, it has proven to be one of the fundamental principles in our present understanding of light and of matter.
The Heisenberg uncertainty principle states that it is impossible to simultaneously determine the location and momentum of particles, such as electrons. Rather, we can predict the probability where electrons are likely to be and areas where they are not likely to be. Consider the blades of a fan. As long as the fan has no kinetic energy, it's easy to see exactly where each of the blades is located. When the blades of the fan start moving, however, this becomes much more difficult. If we shot a very small particle here, it might hit a blade, or it might not. Without a measurement device more precise than our eyes, there is a degree of uncertainty associated with the position of the blade. Through experiments, we can determine that there is a high probability of hitting the blade inside this region, and a very low probability of hitting the blade if we aim out here. Similarly, if we shoot an extremely small particle or photon at an atom, there are regions where it is likely to encounter an electron and others where it is less likely. In this case, however, there is even a further complication. The fan blade is approximately the same size as the object hitting it. So if the photon does hit an electron, the electron is jarred from its original course. When we were looking at the blades of the fan, our eyes could not ascertain the exact position of the spinning fan blade. The measurement tool, our eyes, kept us from taking sufficiently precise readings. Similarly, the tools for detecting electrons limit the accuracy to which we can determine the location of the electron. We can only talk about probabilities of where the electron might be. The exact position and momentum is uncertain.
The Schrödinger Wave Equation. In 1926, the Austrian physicist Erwin Schrödinger used the hypothesis that electrons have a dual wave-particle nature to develop an equation that treated electrons in atoms as waves. Unlike Bohr's theory, which assumed quantization as a fact, quantization of electron energies was a natural outcome of Schrödinger's equation. Only the waves of specific energies, and therefore frequencies, provided solutions for the equation. Together with the Heisenberg uncertainty principle, the Schrödinger wave equation laid the foundation for modern quantum theory. Quantum theory describes mathematically the wave properties of electrons and other very small particles. Solutions to the Schrödinger wave equation are known as wave functions. Based on the Heisenberg uncertainty principle, the early developers of quantum theory determined that wave functions give only the probability of finding an electron at a given space around the nucleus. Thus, electrons do not travel around the nucleus in neat orbits as Bohr had postulated. Instead, they exist in certain regions called orbitals. An orbital is a three-dimensional region around the nucleus that indicates the probable location of an electron. Figure 4-11 on page 101 of your text, or on the screen now, illustrates two ways of picturing one type of atomic orbital. As you will see later in this section, atomic orbitals have different shapes and sizes.
It is very difficult to predict the position of any given electron at any given time. There are, however, regions inside the atom where electrons are likely to be, and other regions where electrons are unlikely to be.
At this point, you should be able to discuss Louis de Broglie's role in the development of the quantum model of the atom, compare and contrast the Bohr model and the quantum model of the atom, and explain how the Heisenberg uncertainty principle and the Schrödinger wave equation led to the idea of atomic orbitals.